Welcome to Science to Sleep By. Tonight, we're going to slow down and step away from the noise of everyday explanations. This is not a lecture, not a test, and not a race to understand every equation. This is a quiet journey into how the universe truly works beneath the surface, at a level far too small to see, but deeply responsible for everything around you. Quantum mechanics often gets described as strange, confusing, or even magical, but in reality is simply the universe behaving honestly, without pretending to fit our everyday intuition. And when we approach it gently, without urgency, it becomes less mysterious and more beautiful. If you're listening from a quiet room somewhere in the United States, perhaps late at night, let this be a moment where curiosity replaces effort. If you like my videos, please subscribe my channel and hit the bell icon. You don't need to visualize math. You don't need to remember names or dates. All you need to do is listen, breathe, and allow the ideas to unfold naturally. Quantum mechanics doesn't describe a chaotic universe. It describes a universe that is subtle, patient, and deeply structured, where certainty softens into probability, and where reality exists as a range of possibilities rather than fixed outcomes. As this talk continues, we'll move slowly. Each idea will rest before the next one begins. Nothing here requires force or concentration. Understanding can happen quietly, even as you drift closer to sleep. At the deepest level of reality, quantum mechanics exists because the universe simply refuses to behave like the solid, predictable world we experience at human scales. For centuries, classical physics worked beautifully by assuming that objects always have definite positions, definite speeds, and definite paths through space and time. A thrown baseball follows a smooth arc. A planet moves along a stable orbit. A clock ticks forward in steady, reliable steps. But as scientists began to look closer, far closer than the eye can see, these comforting assumptions started to quietly fall apart. The universe, it turned out, was not obligated to remain intuitive when examined at extremely small scales. When we talk about the quantum world, we are talking about distances so tiny that everyday comparisons no longer help. Atoms are not miniature solar systems, and particles are not tiny marbles. Instead, they exist in a realm where the concepts of here and there begin to blur. At this scale, energy does not flow smoothly, but arrives in discrete packets, like gentle taps, rather than continuous streams. This is where the word quantum comes from, a reminder that nature, at its foundation, moves in small, indivisible steps rather than seamless motion. Classical physics begins to fail because it assumes that measurement does not disturb what is being measured. In the everyday world, this assumption works well. You can look at a parked car without moving it. You can weigh a book without changing its content. But in the quantum world, observation is never passive. To measure something extremely small, you must interact with it, and that interaction inevitably changes it. Light, used to observe an electron, for example, carries energy and momentum, gently but unavoidably nudging the electron in the process. The act of looking becomes part of the story, a separate, neutral step. This is not a limitation of technology or human skill. Even with perfect instruments, the problem remains. Nature itself has drawn a line between what can be known simultaneously and what cannot. Position and momentum, for example, cannot both be known with complete precision at the same time. This is not because the universe is hiding information from us, but because those properties do not exist in a fully defined way until an interaction forces a choice. Classical physics demands certainty. Quantum mechanics offers honesty. The reason the quantum world feels so unfamiliar is that our brains evolved to survive at human scales, not atomic ones. Our intuition is shaped by gravity, friction, and solid objects. But at the quantum level, gravity is almost irrelevant, friction disappears, and solidity itself is an illusion. What we experience as solid matter is mostly empty space held together by electromagnetic forces and quantum rules. The chair beneath you feels firm, not because it is packed solid with substance, but because the quantum behavior of electrons prevents atoms from passing through one another. Quantum mechanics exists because without it, atoms could not be stable. Classical physics predicts that electrons orbiting a nucleus should continuously lose energy and spiral inward, collapsing the atom in a fraction of a second. But atoms do not collapse. They persist. They form molecules. They build stars, planets, and living beings. Quantum mechanics resolves this by allowing only certain stable energy states, preventing electrons from radiating energy endlessly. In this sense, quantum mechanics is not strange, it is necessary. At small scales, energy behaves differently because nature prefers efficiency over smoothness. Just as a staircase allows you to change height in steps rather than a continuous slope, quantum systems change energy in discrete levels. These levels are not chosen arbitrarily. They emerge from the geometry of the system itself. The size of an atom, the color of light it emits, and the way it bonds with other atoms all arise from these allowed quantum states. Chemistry, biology, and even the warmth of sunlight depend on this quiet, step-like structure of reality. The need for quantum mechanics becomes even clearer when we consider light. Classical physics treated light as a wave spreading smoothly through space. This explanation worked until experiments revealed that light sometimes behaves like a stream of particles, delivering energy in tiny packets called photons. This dual nature could not be explained by classical ideas alone. Quantum mechanics does not force light to choose between being a wave or a particle. Instead, it allows light to be something deeper, an entity whose behavior depends on how it interacts with the world. What we call weirdness in quantum mechanics is often just the universe refusing to simplify itself for our comfort. Probability replaces certainty, not because reality is random, but because reality at this scale contains more possibilities than a single outcome can capture. Before measurement, a quantum system exists in a range of potential states. Measurement narrows those possibilities into one result. This process feels unsettling only because we are accustomed to thinking that the world has already decided everything in advance. Quantum mechanics also exists because time and space behave differently at small scales. Particles do not follow neat, continuous paths. Instead, they explore all possible paths simultaneously, with some paths reinforcing each other and others canceling out. The path, we observe, is not chosen by chance, but emerges from this quiet negotiation among possibilities. What looks random is actually deeply structured beneath the surface, shaped by mathematical relationships that have been confirmed with astonishing precision. From a broader perspective, quantum mechanics is not a replacement for classical physics, but its foundation. Classical laws emerge naturally when many quantum particles act together, smoothing out uncertainty and producing the stable world we recognize. The reason you don't notice quantum effects while walking down the street is not because they are absent, but because they average out at large scales. The classical world is a calm surface floating atop a restless, subtle quantum ocean. Ultimately, the quantum world exists because reality demands it. Without quantum rules, there would be no stable matter, no chemistry, no stars burning steadily for billions of years. There would be no biology, no consciousness, and no one here to ask how the universe works. Quantum mechanics is not an optional layer added to physics, it is the quiet framework that allows existence itself to persist. And when approached slowly, without urgency, it reveals a universe that is not chaotic or hostile, but precise, restrained, and deeply elegant in its smallest details. At the heart of quantum mechanics lies an idea that feels almost poetic in its quiet defiance of common sense. The realization that particles are not merely tiny objects moving through space, but also behave like waves spreading gently across possibilities. This is not a metaphor, and it is not a philosophical trick. It is a direct conclusion drawn from careful experiments, repeated endlessly, always giving the same calm but unsettling answer. Matter, at its most fundamental level, does not commit to being one thing or the other. It exists in a deeper state where the distinction between particle and wave dissolves. In everyday life, the difference between a particle and a wave feels obvious. A grain of sand is a particle. An ocean swell is a wave. One occupies a specific place. the other spreads out. Classical physics insisted that these categories were permanent and exclusive. But as scientists began probing atoms and electrons, they discovered behavior that fit neither category alone. Electrons could strike a detector as localized points, like tiny pellets, yet when allowed to travel freely, they spread out and interfered with themselves, forming patterns that only waves can produce. One of the most revealing demonstrations of this behavior is the double-slit experiment. Not because it is dramatic, but because it is simple. When particles such as electrons pass through two narrow openings and are detected on a screen, they form an interference pattern of light and dark bands. This pattern emerges even when the electrons are sent one at a time, with long pauses between them. Each electron arrives at the screen as a single point, but over time, the collective pattern reveals wave-like interference. The unsettling conclusion is that each electron behaves as though it travels through both slits at once, interfering with itself. This wave-like behavior does not mean the electron is literally split into pieces. Instead, it exists as a spread-out quantum wave that represents a range of possible locations. This wave is not a physical ripple in space, like a water wave, but a mathematical description of probability. It tells us where the electron is likely to be found if we look for it. The wave evolves smoothly over time, exploring multiple possibilities simultaneously, until an interaction forces a specific outcome. When the electron is detected, the wave-like description gives way to a single, localized event. The electron appears at one specific point on the screen, never as a smear or partial imprint. This transition from a spread-out wave of possibilities to a single observed result is one of the central features of quantum mechanics. It does not imply that the electron suddenly becomes real only when observed, but rather that its wave-like nature governs how outcomes are distributed across many trials. The idea that matter behaves like a wave was not introduced arbitrarily. It arose from the realization that light, once thought to be purely a wave, also behaves like a particle. This symmetry hinted at a deeper truth. Wave-like and particle-like behavior are not properties of objects themselves, but of how they interact. When light exchanges energy in discrete packets, it looks like a particle. When it spreads and interferes, it looks like a wave. Matter follows the same rules, guided by the same underlying principles. Wave-particle duality does not mean that particles switch back and forth between two identities. Instead, quantum objects exist in a unified state that cannot be fully captured by classical labels. The wave describes how the particle moves and evolves through possibilities, while the particle describes how it interacts when measured. Both descriptions are necessary, and neither is complete on its own. Together, they form a more accurate, though less intuitive, picture of reality. At a deeper level, the wave nature of particles explains why atoms have specific sizes and shapes. Electrons in an atom do not orbit the nucleus like planets. Instead, they form standing wave patterns around it. These patterns arise because only certain wave shapes can remain stable without canceling themselves out. Each allowed pattern corresponds to a specific energy level, and transitions between these levels produce the light emitted or absorbed by atoms. The colors of the periodic table, the glow of neon signs, and the warmth of sunlight all trace back to this quiet wave behavior. The wave nature of matter also explains why particles can sometimes pass through barriers they seemingly should not. Quantum tunneling occurs because a particle's wave does not abruptly end at an obstacle. Instead, it gradually fades, allowing a small probability that the particle will appear on the other side. This is not a violation of energy conservation, but a natural consequence of wave behavior. Tunneling plays a crucial role in nuclear reactions within stars and in technologies such as semiconductors and scanning tunneling microscopes. Despite its strangeness, wave-particle duality does not introduce chaos into the universe. On the contrary, it introduces remarkable consistency. The equations governing quantum waves have been tested to extraordinary precision, predicting experimental outcomes with unmatched accuracy. The apparent randomness arises not from disorder, but from the fundamental role of probability in determining individual outcomes. Over many events, These probabilities produce stable, predictable patterns. As systems grow larger, the wave nature of matter becomes increasingly difficult to observe. Interactions with the environment cause quantum waves to lose their coherence, effectively locking particles into well-defined states. This process explains why tables, chairs, and people do not exhibit obvious wave behavior. The quantum waves are still there, but their delicate patterns are washed out by countless interactions, leaving behind the solid world we recognize. Understanding particles as waves is not meant to unsettle, but to deepen our sense of connection to the universe. It reveals that even the smallest pieces of matter are not isolated points, but extended presences shaped by relationships and possibilities. The universe, at its foundation, is less like a machine made of rigid parts, and more like a quiet symphony of overlapping patterns, each contributing to the stability and beauty of the whole. When approached gently, this idea does not disrupt sleep, it invites a sense of calm wonder, reminding us that reality is richer, softer, and more interconnected than it first appears. One of the most profound shifts introduced by quantum mechanics is the quiet acceptance that certainty is not woven into the fabric of reality. In the classical world, certainty feels natural and unavoidable. A ball has a precise position, clear speed, and a predictable future path. If we know enough about the present, we believe we can calculate the future with confidence. This belief shaped science for centuries and gave rise to the comforting idea that the universe is a perfectly predictable machine. Quantum mechanics gently but firmly reveals that this picture was never complete. At the quantum level, nature does not assign exact values to all properties at all times. Instead, it offers ranges, tendencies, and probabilities. This is not because particles are poorly defined or incomplete, but because the universe itself operates in a way where some details simply do not exist simultaneously in a sharp, definite form. Position and momentum, for example, are not hidden values waiting to be uncovered. They are complementary aspects of reality, and sharpening one inevitably softens the other. This realization is often associated with the uncertainty principle, but its meaning is frequently misunderstood. It does not say that our instruments are clumsy or that scientists lack precision. It says that the act of defining certain properties limits the definition of others. The universe enforces this balance not as a restriction, but as a structural feature. Just as a wave cannot have both a perfectly defined location and a perfectly defined wavelength, a quantum system cannot possess absolute certainty in all measurable aspects at once. Probability enters quantum mechanics not as a sign of ignorance, but as a fundamental language. When we describe a particle's position or energy, we are not describing a single outcome, but a spread of possible outcomes, each with a specific likelihood. These probabilities are not guesses. They are precise and testable. Repeating the same experiment many times produces patterns that match quantum predictions with remarkable accuracy. The uncertainty lies in individual events, not in the overall structure. This shift from certainty to probability challenges a deeply ingrained human instinct. We are used to thinking that things either are or are not, that events either happen or do not happen. Quantum mechanics replaces this rigid binary view with a softer gradient of possibility. Before measurement, a system exists in a combination of potential states, each contributing to the final outcome. This does not mean that reality is undecided or confused. It means that reality contains more information than a single, definite answer can express. The idea that outcomes are probabilistic does not make the universe lawless. On the contrary, quantum mechanics is one of the most rigorously structured theories ever developed. Its equations determine how probabilities evolve over time, how they interfere, and how they combine. What appears random at the surface level is governed by deep mathematical consistency underneath. The universe is not rolling dice carelessly. It is following rules that operate beyond classical intuition. This probabilistic nature becomes especially clear in radioactive decay. A single unstable atom cannot be predicted to decay at a specific moment. There is no hidden clock ticking inside it. Yet, when we observe a large collection of such atoms, the decay follows a precise statistical pattern, allowing us to define half-lives with extraordinary reliability. The unpredictability of individual events coexists peacefully with the predictability of large-scale behavior. Quantum probability also reshapes our understanding of cause and effect. In classical physics, a cause leads to a single, inevitable outcome. In quantum mechanics, a cause leads to a range of possible outcomes, each weighted by probability. The cause does not vanish. It becomes a distributor of possibilities. This does not weaken causality, but refines it. The future is not a single path carved in stone, but a branching landscape where some paths are far more likely than others. The illusion of certainty arises because, at larger scales, probabilities average out. When trillions of particles interact, their individual uncertainties cancel each other, producing stable, predictable results. This is why we can rely on bridges to stand, clocks to tick, and seasons to change. The uncertainty is still there, but it is spread so thinly that it becomes invisible. Classical certainty is not fundamental. It is an emergent calm that arises from underlying quantum fluctuation. Even measurement itself reflects this balance between certainty and probability. When we measure a quantum system, we do not uncover a pre-existing definite value. We participate in an interaction that produces a specific outcome from a range of possibilities. This outcome is not arbitrary. It follows the probability distribution defined by the system's prior state. Measurement, then, is not about revealing hidden facts, but about completing a process. This perspective invites a quieter way of thinking about reality. Instead of demanding exact answers at all times, quantum mechanics encourages patience with uncertainty. It suggests that the universe is not built on rigid absolutes, but on flexible structures that allow stability without eliminating variation. This balance is not a weakness. It is what makes complexity possible. In the context of the natural world, this probabilistic foundation allows atoms to form molecules, molecules to form life, and life to adapt rather than remain fixed. Absolute certainty would freeze the universe into monotony. Probability introduces room for change while preserving order. The world is not less real because it is uncertain. It is more resilient. As this idea settles in, it becomes less unsettling and more soothing. Certainty is heavy, demanding constant control. Probability is lighter, allowing outcomes to emerge without force. The quantum universe does not insist on knowing everything in advance. It unfolds gently, moment by moment, guided by likelihood rather than command. And in that quiet unfolding, there is a deep sense of balance, one that mirrors the calm rhythm of nature itself. Inviting the mind to rest rather than struggle against the unknown. One of the most misunderstood ideas in quantum mechanics is the statement that observation changes reality. This phrase often sounds dramatic, as if the universe waits for a human mind to look at it before deciding what to do. In truth, quantum mechanics makes a much quieter and more precise claim. It is not consciousness that alters the outcome of an experiment, but interaction. To observe something at the quantum level is to physically interact with it, and that interaction becomes inseparable from the behavior being observed. In the classical world, observation can be almost passive. You can watch the moon through a telescope without affecting its orbit. You can listen to the sound of rain without changing the weather. These experiences shape our intuition, leading us to believe that reality exists fully formed and unaffected by measurement. Quantum systems do not grant us this luxury. At extremely small scales, there is no such thing as a detached observer. Every attempt to gain information involves an exchange of energy, momentum, or some other physical influence. Consider how one might observe an electron. You cannot simply look at it in the ordinary sense. You must use something like a photon to interact with it. That photon carries energy, and when it collides with the electron, it transfers some of that energy. The electron's state changes as a direct result of being observed. This is not a flaw in experimental design, but a fundamental reality of the quantum world. The system and the measuring device become part of a single, combined process. This is why the concept of measurement in quantum mechanics is deeper than simply reading a value from an instrument. Measurement is an event, not a passive recording. Before measurement, a quantum system is described by a wave-like state that encodes multiple possibilities. During measurement, this wave-like description gives way to a specific outcome. The result is not chosen arbitrarily. It emerges from the structure of the system and the nature of the interaction. The famous double-slit experiment illustrates this idea in a particularly clear way. When particles such as electrons pass through two slits without any attempt to detect which slit they go through, an interference pattern appears on the screen, revealing wave-like behavior. When a detector is placed to determine the particle's path, the interference pattern disappears. The key point is not that someone is watching, but that the detector interacts with the particle. The interaction changes the conditions under which the particle evolves, and the behavior adjusts accordingly. It is tempting to imagine that the particle somehow knows it is being observed and changes its behavior in response. Quantum mechanics does not support this interpretation. Instead, the particle's wave-like state becomes entangled with the measuring device. Information about the particle's path becomes encoded in the environment, destroying the delicate interference effects. What looks like a sudden change is actually a gradual loss of coherence as the system interacts with its surroundings. This process, known as decoherence, helps explain why the classical world appears stable and definite. In everyday life, objects are constantly interacting with air molecules, light, and thermal vibrations. These interactions rapidly eliminate quantum superpositions, leaving objects in well-defined states. The world looks solid and certain, not because quantum mechanics stops applying, but because interactions happen so quickly and so thoroughly that quantum possibilities are effectively suppressed. Measurement, then, is not a mystical collapse triggered by awareness. It is the natural outcome of interaction in a complex environment. When a quantum system becomes sufficiently entangled with its surroundings, the range of possible outcomes narrows until only one is effectively realized. From our perspective, it appears as though the system has chosen a definite state. From the universe's perspective, it has simply followed its rules. This understanding reshapes the role of the observer. We are not external judges standing outside reality. We are physical systems embedded within it, subject to the same laws as everything else. When we observe, we participate. Our instruments, our bodies, and even the air around us become part of the quantum story. The boundary between observer and observed blurs, revealing a more interconnected picture of existence. The idea that observation changes reality also highlights the limits of what can be known simultaneously. By choosing to measure one property, we necessarily disturb others. Measuring position with high precision disrupts momentum. Measuring energy precisely requires time. These trade-offs are not inconveniences, but reflections of how information is structured in the universe. Knowledge comes with a cost, and that cost is built into reality itself. Despite its unsettling reputation, this principle introduces a kind of gentleness into our understanding of nature. Reality is not rigid and fixed before we arrive. It is responsive, shaped by relationships and interactions. Outcomes emerge through engagement, not isolation. This does not diminish objectivity. It enriches it by acknowledging that observation is always part of the physical process. When approached slowly, this idea becomes calming rather than disturbing. It suggests that the universe is not a cold, indifferent machine, but a dynamic system where participation matters. Every interaction leaves a trace. Every measurement completes a process. The world is not waiting to be seen, but continuously forming itself through countless quiet interactions. In the end, observation in quantum mechanics is a reminder of our place within the universe. We are not separate from the phenomena we study. We are woven into the same fabric, governed by the same rules. Reality unfolds through interaction, and understanding rises through participation. This perspective invites humility and calm, encouraging us to observe without the need for control, and to accept that knowing something always involves becoming part of its story. Entanglement is one of the quietest yet most profound ideas in quantum mechanics, revealing a universe where separation is not as complete as it appears. At first glance, the concept seems almost impossible, Two particles, once connected, remain linked even when separated by vast distances. Measure one, and the state of the other is instantly determined, no matter how far away it is. This description has often been dramatized as spooky action at a distance, but beneath the mystery lies a deeply structured and surprisingly gentle feature of reality. To understand entanglement, it helps to begin with the idea of a shared quantum state. When two particles interact in certain ways, their properties become intertwined. Instead of each particle having its own independent description, the system must be described as a whole. The particles no longer carry separate identities in the classical sense. Their properties exist only in relation to each other. Even when they move apart, this shared description remains intact. What makes entanglement so striking is not that information travels faster than light, but that the information was never separate to begin with. When an entangled pair is created, the outcome of certain measurements is not determined for either particle individually. Instead, the outcomes are correlated. Measuring one particle does not send a signal to the other. It simply reveals a relationship that was already present. The universe does not need to communicate across space. It already knows how the pieces fit together. This challenges our everyday intuition, which assumes that objects carry their own independent properties wherever they go. In the classical world, a coin in your pocket has a definite face, whether or not anyone looks at it. In the quantum world, entangled particles do not carry fixed values in isolation. Their properties are defined only when compared. The certainty lies in the relationship, not in the individual parts. Experiments have confirmed entanglement with remarkable precision. Pairs of photons, electrons, and even larger systems have been shown to exhibit correlations that cannot be explained by classical theories. These experiments rule out the idea that particles simply carry hidden instructions telling them how to behave. Instead, the results suggest that nature itself is non-local in a subtle but precise way. The universe allows connections that transcend spatial separation without violating causality. Entanglement does not allow faster-than-light communication, and this is crucial. Although the outcomes of measurements are correlated, they are individually random. No usable message can be sent through entanglement alone. This preserves the structure of relativity while expanding our understanding of connection. Space still limits communication, but it does not limit correlation. The universe respects speed limits while quietly redefining what it means to be connected. At a deeper level, entanglement suggests that the universe is not built from independent building blocks, but from relationships. The fundamental unit of reality may not be a particle, but a connection. This perspective shifts the focus from objects to patterns, from isolated things to shared structures. The world becomes less like a collection of separate points, and more like a woven fabric, where threads remain linked even when stretched apart. Entanglement also plays a crucial role in stabilizing the physical world. The behavior of electrons in atoms, the formation of chemical bonds, and the properties of solids all depend on entangled states. Without entanglement, matter would not have the richness or stability we observe. The solidity of a table, the conductivity of a wire, and the softness of a pillow all trace back to entangled interactions at the microscopic level. In recent years, entanglement has moved from a philosophical curiosity to a practical resource. Technologies such as quantum computing and quantum cryptography rely on entangled states to perform tasks that would be impossible with classical systems alone. Quantum computers use entanglement to explore many possibilities simultaneously, while quantum encryption uses it to detect eavesdropping with absolute certainty. These applications do not exploit mystery, but precision. They work because entanglement follows strict and reliable rules. Despite its power, entanglement remains fragile. Interactions with the environment can easily disrupt it, a process similar to the loss of coherence in other quantum systems. This fragility explains why entanglement is not obvious in everyday life. The world around us is too noisy, too interactive, for delicate quantum correlations to survive for long. Yet even fleeting entanglement leaves its mark, shaping how systems behave and evolve. From a broader perspective, entanglement invites a more connected view of existence. It suggests that separation is not absolute, that the universe retains memory of interactions long after objects move apart. This does not mean everything is permanently linked to everything else, but it does mean that connections matter. History leaves traces, and interactions have lasting consequences at the deepest levels. When approached gently, entanglement feels less like a paradox and more like a quiet truth. The universe is not a collection of lonely particles drifting through empty space. It is a network of relationships, constantly forming, dissolving, and reforming. Distance does not erase connection. It merely changes how that connection is expressed. In the stillness of reflection, entanglement can feel almost comforting. It suggests that nothing is ever entirely alone, that interactions leave echoes, and that the universe remembers its own past. Reality is not stitched together loosely, but held in place by subtle, enduring bonds. As the mind settles into this idea, the strangeness softens, revealing a cosmos that is not chaotic or disconnected, but quietly unified beneath the surface. Resting in a balance of relationship and form, quantum mechanics often feels distant from everyday experience. Yet it is precisely the set of rules that allows the familiar world to exist in the first place. The quiet laws governing particles and waves do not remain trapped in laboratories or equations. They scale upward, layer by layer, until they form the stable, predictable reality we inhabit. The chairs we sit on, the air we breathe, and the warmth of sunlight on our skin are all expressions of quantum behavior averaged over countless interactions. The everyday world is not separate from the quantum world. It is built from it. At the level of atoms, quantum rules determine how electrons arrange themselves around nuclei. These arrangements are not arbitrary. They define the size of atoms, the way they bond, and the kinds of molecules they can form. Chemistry, which often feels like a classical science of reactions and formulas, is in fact a direct consequence of quantum mechanics. The strength of a chemical bond, the shape of a molecule, and the speed of a reaction all arise from the wave-like nature of electrons and the probabilities governing their behavior. As atoms combine into molecules, quantum effects continue to guide the process quietly. The folding of proteins, the structure of DNA, and the efficiency of enzymes all depend on quantum interactions at the smallest scales. Life does not override quantum mechanics. It relies on it. Even processes like photosynthesis make use of subtle quantum coherence to transfer energy efficiently. Biology, at its core, is quantum mechanics expressed through chemistry over long periods of time. When enormous numbers of particles interact, their individual uncertainties begin to average out. This averaging process is what gives rise to classical behavior. Objects acquire well-defined positions and motions, not because quantum rules disappear, but because their effects become collectively stable. The randomness of individual particles smooths into reliability when billions of them act together. This is why a glass falls when dropped, and why a pendulum swings predictably. Classical physics emerges as a calm approximation, valid when quantum fluctuations are no longer noticeable. Temperature plays a key role in this transition. At higher temperatures, particles interact more frequently and more energetically, rapidly disrupting delicate quantum correlations. This constant interaction locks systems into definite states, suppressing wave-like behavior. At very low temperatures, however, quantum effects can resurface on large scales. Superconductors, superfluids, and Bose-Einstein condensates reveal that quantum mechanics never truly goes away. It simply hides until conditions allow it to re-emerge. Technology offers some of the clearest demonstrations of how quantum rules shape everyday life. Semiconductors, which power computers and smartphones, rely on quantum energy levels within materials. Lasers, used in medicine, communication, and entertainment, function because electrons transition between quantized states. Magnetic resonance imaging, GPS systems, and even modern clocks depend on quantum precision. These technologies work not despite quantum mechanics, but because of it. The stability of matter itself, is a triumph of quantum rules. Without them, electrons would collapse into atomic nuclei, and atoms would cease to exist. The fact that matter has size, structure, and resilience is a direct consequence of quantum principles such as the exclusion principle, which prevents identical particles from occupying the same state. This principle gives rise to the rigidity of solids and the diversity of chemical elements. The solidity of the world is, paradoxically, rooted in the impossibility of perfect overlap at the quantum level. On cosmic scales, quantum mechanics also leaves its imprint. The light from distant stars carries the signature of atomic transitions. The formation of elements in stellar cores depends on quantum tunneling. Even the structure of the early universe bears traces of quantum fluctuations stretched across space by cosmic expansion. The largest patterns in the universe emerged from the smallest quantum variations, amplified over billions of years. Understanding how quantum rules build the everyday world offers a sense of continuity rather than disruption. There is no sharp boundary where the quantum realm ends and the classical world begins. Instead, there is a gradual transition, a blending of behaviors as systems grow larger and interactions become more complex. The universe does not switch rulebooks. It uses the same rules everywhere, allowing different behaviors to emerge naturally at different scales. This perspective brings a quiet reassurance. The unpredictability of quantum mechanics does not undermine the stability of daily life. On the contrary, it is the reason stability exists at all. Order arises not from rigid certainty, but from flexible rules that allow balance and adaptation. The universe maintains structure without freezing into immobility, change without collapsing into chaos. As this journey through quantum mechanics comes to a close, it becomes clear that the theory is not a collection of strange exceptions, but a deep and consistent description of reality. The same principles that govern invisible particles also shape the world of touch, motion, and time. Nothing about everyday life escapes the quantum foundation beneath it, and as the mind begins to rest, this realization can feel gently comforting. Beneath the noise of daily experience lies a universe that is precise, patient, and quietly reliable. Every breath, every heartbeat, every moment of stillness is supported by rules that have been operating without interruption since the beginning of time. The quantum world does not demand attention or effort. It simply holds everything together. So as this thought settles in, there is nothing left to analyze or control. The universe is doing its work effortlessly, just as it always has. You can allow your thoughts to slow, knowing that the same gentle laws shaping stars and atoms are also guiding this moment. In that understanding, the mind can soften, curiosity can rest, and sleep can arrive naturally, carried by the quiet certainty that reality, at every scale, is already in balance. As we come to the end of this journey through quantum mechanics, there is no final equation to memorize and no single image that captures everything we have explored. What remains is something quieter and deeper, a sense of how the universe chooses to exist beneath appearances. Quantum mechanics does not replace the everyday world we know. It gently explains how that world is able to exist at all. It shows us that certainty, solidity, and stability are not fundamental givens, but achievements emerging from rules that are subtle, probabilistic, and deeply interconnected. We began by stepping away from the comfort of classical intuition and allowing the quantum world to speak in its own language. A language where particles behave like waves, where outcomes are described by likelihood rather than guarantee, and where observation is not passive, but participatory. At first, these ideas can feel unsettling. They challenge the assumption that reality is fixed and independent of interaction. Yet, as we have seen, this flexibility is not a weakness. It is the reason atoms hold together, why chemistry works, and why the universe is capable of complexity rather than collapse. Quantum mechanics invites us to loosen our grip on absolute certainty. It teaches us that not everything meaningful needs to be precisely defined at all times. In the quantum world, possibilities coexist until interaction brings one forward. This is not confusion. It is potential. The universe allows room for outcomes to emerge rather than forcing them into place too early. And in that openness, structure forms naturally, without rigidity. One of the most profound lessons of quantum mechanics is that separation is never complete. Through entanglement, we see that connection can persist across distance, not through signals or force, but through shared history. The universe remembers its interactions. It carries relationships forward even as objects drift apart. This does not diminish individuality, but places it within a larger web of meaning. Everything is shaped not only by what it is, but by what it has touched. Perhaps most quietly powerful is the realization that we are not outside this system. We are part of it. Our measurements, our instruments, and even our bodies are made of the same quantum fabric we seek to understand. Observation is not domination, but participation. To know something is to interact with it, and that interaction completes a process rather than interrupting it. This places us back into the universe, not above it. And despite its reputation for strangeness, quantum mechanics is not chaotic or hostile. It is one of the most precise and reliable frameworks ever discovered. Its predictions match experiments with extraordinary accuracy. The randomness it introduces is not lawlessness, but freedom within structure. On large scales, this freedom averages into the calm reliability of everyday life. The floor remains solid. The sun continues to rise. The body breathes without instruction. Seen this way, the quantum foundation of reality becomes deeply reassuring. Beneath the noise of daily concerns and surface-level unpredictability lies a universe that is remarkably consistent. Every moment is supported by rules that have held since the earliest instants of time. Nothing about this moment is accidental or unstable. It is balanced by probabilities that have proven their reliability across billions of years. As this understanding settles, there is no need to hold on to every detail. The equations can fade. The concepts can soften. What matters is the feeling that reality is not fragile. It is adaptive. It does not demand certainty from us, only participation. The universe does not rush, and neither must we. So as this exploration comes to rest, allow the mind to do the same. Let curiosity quiet itself. Let questions remain unanswered without tension. The quantum world will continue its work regardless, holding atoms together, guiding light across space, and shaping the gentle order beneath all things. In that knowledge, there is nothing left to solve, nothing left to chase. Only the calm understanding that existence, at its deepest level, is already complete and that it is safe to let go and simply rest. Good night.